And you'll kind of figure this out on Monday. Hello? Hi. Hi. I could, if they would let me out early, I could do it. I don't know, that would have to be something that they would have to. I checked with Mr. Randall. Yeah, you just give me a call back. Oh, he does, well, that's a good deal. Yeah, I'd be more than willing to help out and do whatever I need to. That would be great. Okay, thanks. So, there's some things that mix and some things that don't. And it's a real easy concept. Do you guys remember when we talked about polar bonding? You guys remember that? And hydrogen bonding. Okay. Let me talk to you a little bit about those two. So you don't have to write this down because you've seen this before. All right? So this is not something that you have to write down. So here's water. And water has a situation where, man, the eraser's big. You have a situation where this side of the molecule is slightly positive and this side is slightly negative. Okay? And I relate this as an analogy. I don't know if it's the greatest analogy to use, but I think some of you can identify it with it. So these polar molecules tend to hang out together. Okay? And so we have at school certain groups of students that tend to hang out with one another. You can kind of go down the lunchroom, you can kind of see what, certain tables are comfortable sitting with each other all year long or all semester long, and they get along just fine, and you just have different groups that tend to hang together. And if you would be a person that would sit down with that group on a day that you normally don't sit with, that would be maybe a little bit more uncomfortable situation, right? I mean, you don't know anybody at that table, and you just sit down there at that table. And then, whether they're welcoming or not, these molecules tend to want to stay together because there's attraction between these molecules due to polar bonding. We have opposites attract. Positives attract the negatives. So we have all these water molecules that will tend to stay together. So we have that attraction. It's called polar or dipole-dipole interaction, and also hydrogen bonding. So let's say that we have a molecule that we want to introduce into this group, and this molecule is, and I'm not going to make this too long, and let's say this molecule has no polar bonding. So the bonding between carbon and hydrogen would be basically nonpolar. And this molecule tries to get in between these other molecules. Is it going to get a chance to get in between? What do you think? You think it can get in between where there's an attraction, and this doesn't have no attraction because this is called nonpolar molecule because it doesn't have polar bonding. And these are polar molecules. So do you think this one's going to get in there? Nope. So what's going to happen? You're going to have two layers, right? You're going to have two layers. The one that's most dense will be on the bottom. The one at least density will be on top. So you'll have at least two layers if it's a combination of a polar, nonpolar substance. Okay. So does anybody in here ever painted with an oil-based paint? Okay, or fingernail polish would be kind of an oil-based paint. And you get some of that on your hand. What do you need to do to wash that off of your hand? Can you use water to wash it off? Nope. What's that?
Nail polish remover.
So the nail polish remover, what it is, it's non-polar. The paint, since it's oil-based, oil is non-polar. So you have to have something that's non-polar to be able to mix with the other non-polar substance. Okay? Water won't do it. Water will not do it because it can't mix. It won't mix in between. And so we're going to talk, when you guys do your lab, more about polar and non-polar characteristics. Okay? We'll bring this back up on Monday before you do your lab. But polar substances can only dissolve other polar molecules. So what water, can you think of something that's a molecule that water dissolves? Think of a molecule.
Salt.
Okay? Now salt is actually not molecular, it's ionic. So water will break apart ionic compounds because there's positives and negatives in an ionic compound. So this side would be attracted to the negative, like chlorine, sodium chloride would be attracted to chlorine and pull it away. And then oxygen would be attracted to sodium and pull it away. Okay, and that discusses that in this chapter. And so polar molecules will dissolve ionic substances, but can you think of something molecular that's made out of hydrogens, carbons, oxygens, that will mix with water? You think any salt? Yes.
Ethanol.
Ethanol will mix with water because it's polar. Okay, here's ethanol. So ethanol is this molecule right here because it has a polar end. Okay, this is the polar end for ethanol. Right here is polar. So this polar end can get in there and can mix in that solution. Okay? Give me 5 minutes and we'll get it down to you. I'll get it down to you. Okay?
I'll be down.
And you're going to be in the media?
Yeah.
Okay. So that would be non-polar. Or I'm sorry, this would be polar. So it would mix in. Anything else, a solid that can dissolve in water?
Sugar.
Sugar. Sugar is going to have a polar characteristic. Okay? All right, so we'll talk about that, but just an idea about non-polar and polar and how they work. Okay? The last thing I want to talk about is this thing called Henry's Law. If you want to write this down, we'll talk a little bit about Henry's Law. If you guys want to write that down, I'll do the same. Okay? Henry's Law says the solubility of a gas in a liquid. So how it dissolves. Is directly proportional to the partial pressure of that gas on the surface of the liquid. So what that means is that if you have a pop like this, and you want to dissolve more CO2, make it more carbonated, then you have to apply more pressure of that gas above the liquid. So there's a little bit of space up here in pops. Okay, they're not filled all the way. Why is there that space? And why do you have that space? It's because they want to put CO2 up there. And they want to compress that CO2 so that if they compress that CO2, they can make this more carbonated. Okay? So what I've read and what I understand is that pop usually has about 4 or 5 times pressure that's in the room. Okay, so if the pressure in the room is 1 atmosphere, the pressure on top of the CO2 above here is 5 atmospheres. So they apply. Now, can it be O2 above the gas? O2? Mm-mm. Not very close. Okay, thanks. Okay? So the pressure above the gas has to be CO2. It can't be oxygen. It can't be, some of these other things that's not CO2. It has to be CO2. So it has to be of that gas. And then we can dissolve more of it. Okay? So I'm going to do a demonstration here in a second with the vacuum pump. Because the vacuum pump, I can control pressure on the outside of a sample of liquid that's got a gas dissolved in it. Okay? And so this setup, I'm going to show you the setup, and we're going to do one example, really all we need to do. Because it's real similar to what we did yesterday. And Henry's law will be solubility of a gas, we'll go S1, over pressure, P1. And then we'll go S2 over the pressure of 2. Because we know that's direct. Anytime you take one variable and divide by the other, that gives you a slope on a line. It seems like chemistry, we got a lot of direct relationships. And that's good, because once you've seen one or two, then you can adapt all the other ones. Okay? So, where do you get your solubilities? Okay? If you turn in your book to page 410, which is back a page, at the bottom we have these solubilities. And it says, those two, it says, not like the solids, it says SP. What do you think SP stands for? At SP. Standard pressure. So what's standard pressure?
1 atm.
1 atm. So let's just take one at 0 degrees Celsius. Let's say this pop is right at 0 degrees Celsius. It's been in a refrigerator, set it right at 0. And you say, why hasn't it frozen? Well, it's got sugar in it, and sugar will lower the freezing point. Okay? If you didn't know that, that happens. That's called a colligative property, but we don't talk about that right now. But sugar lowers the freezing point. So we'll say it's at 0 degrees Celsius, okay? And so we're going to write that solubility down. That solubility is 0.335 grams per 100 grams of water. So this is what students will mess up, is that they'll divide this 100 into 0.335, but this is just the solubility. We put that over 1 atm. Okay? Well, let's see what pressure is on this pop if it's 5 atmospheres. If this is exactly 5 atmospheres. So we're going to go, all right, now we're going to increase it to 5 atmospheres. And then we're going to solve for the solubility per 100 grams of water. Okay, what would that be? How many grams are we talking about? So the solubility is what? 1 point, 2 more digits, 6, 7 grams per 100 grams of water. So I have in here about 3.5 times that amount. So the amount of carbon dioxide in grams in here, if that was true, would be between 5 and 6 grams. More towards 6 grams. Well, around 5 grams of CO2 in here. Okay. So what happens when I open this up it's going to start bubbling, right? Because now it's under a different pressure and it can't hold as much. So if you leave it out and let it sit under 1 atmosphere, guess how much you're going to have left in it if you leave it sit out, and it tastes flat, right? Because you only have 0.335 grams of it, where before, per 100 grams, you had 5 times that amount. So that's why it tastes better. Fizzes, they have that effervescence that you have with it. Okay? So what I'll do is demonstrate putting it under 0 pressure. See, it's already coming out. Now, if I poured this and we were under 5 atmosphere pressure, do you think you get that bubbling? No. It poured just like water. Okay? You wouldn't have any fizzing or anything. Okay? So I'm going to go ahead and put this in here. And we're now at 0 pressure, how much CO2 can dissolve? None. None. You can have 0. Okay? You can't have any. So we're going to go ahead and reduce the pressure. Got to plug it in first.